Hi guys, welcome to tutorial 4, question 1. Let's do this. As always, I want to put the question right down here, pause the video, read it over yourself, and then we're going to attempt it together. Now before we start number 1, I do want to clarify this because I didn't know this either. Well, I mean, it kind of didn't make sense to me either, but just double checking. At the beginning it says, assume that n is a power of 2. Just to clarify, that means that we're going to assume that n is even, so that, if you look at the function, when it says n divided by 2, we don't have to worry about, running into an issue of decimals, right? So we're just going to make that assumption that n is even. All right, so the first thing we're going to do is that, we're going to substitute a bunch of times, We're going to, and when I say substitute a bunch of times, I'm not talking about the one that says if n is equal to 1 and that's 3, because, what are you going to substitute? I'm talking about the second one when n is larger than or greater than 1, when it says for fn over 2 plus n. I'm going to put that right there. And we're going to substitute the ones, which, we're going to make sure that, we do a bunch of times. And then, first case is going to be fn equals to 4fn over 2 plus n. That's standard. That comes from the definition. The second time you're going to do it, you're going to reapply that to the f over n over 2 inside the one that we just got. And that's going to be, 4 times 4f n over 4 plus n over 2, because everything divides by 2, plus n. And then, you algebraically try to get everything cleaned up. You're going to end up with 16f n over 4 plus 2n plus n. Again, I'm going to put it right over here. You do it a third time, you're going to get, 16f n over 4 plus 2n plus n, and then you replace the n over 4 with the new version of what's going to be, which is 4f n over 8 plus n over 4, and then, you clean that up again. Again, I'm going to put it right over here. It's going to be 64fn over 8 plus 4n plus 2n plus n. And I could have cleaned up the end up part, but I just, there is a reason why I didn't. And, once you do it a bunch of times, the idea is as you're doing this to look for a pattern. You know what I mean? And when it comes to this case, after thinking about it a little while, a few minutes, you're going to see that pattern. And that pattern is that 4 to the power of k, fn over to the power of, let me say that again. 4 to the power of k times fn over 2 to the power of k, that plus n times, in brackets, summation of I equals to 0 to k minus 1, and then 2i in the front, close bracket. I'm going to, again, put it right over there. And that pattern, to me, it matches all those times that we did substitution. The one that we did it once, the one that we said second, and the one that we did it third. Now, we've got that potential, pattern for ourselves right now, right? And we're pretty certain that's the one that works, right? All right, okay, great. Now, one of the things that we have to take a look at is that, all right, let's say, you keep dividing this thing. We're doing n over 2's over and over and over again from the definition, right? There's got to be a time where it's going to hit 1. I mean, think about it. Any even number, because that's the assumption we made at the beginning. If you keep dividing it and dividing it and dividing it and dividing it, at the end of the day, at some time, it's going to hit 1. Because, 2 divided by, 2 is 1. And, we're going to say, all right, okay, fine. N over 2 to the power of k, because we don't know what k is yet, right, equals to 1. And that's what we want to figure out, what k is, right? So we're going to say, all right, fine, that makes sense. How are we going to solve that? Okay, you're going to bring the denominator up, right? So it's going to be n equals 2 to the power of k. And if you remember, we can just say that the way we can write that is that, all right, k is equal to log of n. And as you remember, by default in this course, the base of log is 2. Exactly. Now that we have our pattern and we know what k is going to be, we're going to plug it in, right? And it's going to be 4 to the power of log n, and then times f1, because we're replacing n over 2 to the power of k with 1, plus n and the summation that goes from 0 all the way to k minus 1. We're not going to replace that k yet. Just hold on. Obviously, you're going to see the entirety of it, and you're going to see why I did that. And then, as we keep going forward, f of 1 is 3, obviously, and that's going to be multiplied by 4 log n. You can see that in the second step. Plus n, and the summation remains the same, and then we're going to attack it in the next line. And then, in the third line, we're not going to touch the 3 times 4 log n thing. We're just going to go and deal with the summation one. And the summation, there's an identity for it from what I know, and that's going to equal to 2 to the power of k minus 1. Now, this is where we're going to change that k to log of n that we talked about. It's so much cleaner if you do it like that. And maybe it also works out. It also works out the other way. It really doesn't matter. But we're gonna, as you can see, we're gonna replace that on the fourth line. So now it becomes 2 to the power of log n minus 1. We go to the fifth line, and this is a little hack that I did. The 4 to the power of log n, let's make that 2 to the power of 2 to the power of log n, if we can do that, if that's a possibility. Why am I doing that? Mostly because in the fifth line, I can come out and say, all right, bring the log n into the bracket, bring the 2 out of the bracket, right? And, as you go to the sixth line, based on an identity, which I'm going to include right over here, which is a to the power of log base ab equals b. Now, and that's why that 2 to the power of log n to the power of 2 is going to equal to n squared. So it's much more simplified. Now, I know I skipped over the whole what's happening on the right side, which is n times 2 to the power of log n minus 1. That's the last we left it. All right, okay. Well, 2 to the power of log n, based on the same identity that I just talked to you about, because log, again, remember that. In this class, the base is 2. It's going to be n. Still, it's going to be n, because 2 to the power of log of base 2 and then n, based on the same identity, is going to equal to n. So it's going to be n times n minus 1, and then, it's going to keep going forward, and it's going to be n squared minus n. And that's how we have 3n squared plus n squared minus n in the second last line. And then it's just going to come down to 4n squared minus n. Now that we do have 4n squared minus n, fn equals to that. That's the closed form. Technically speaking, we're done. Technically speaking. But because this is a tutorial and, I need you guys to understand. And again, this is an important part too, because we might actually ask you this too. That is, we have to prove this is correct using mathematical induction. And, that sounds very reasonable to me. It makes sense. And we're going to use complete induction. We're going to start with a base case. We're going to say, all right, we know that f of 1 is equal to 3, right? Does this equal to 3? Well, yes, 4n squared minus n equals to 3 when n is equal to 1. Boom. Base case over. Induction hypothesis. We're going to suppose that f n over 2 equals to 4 times n over 2 squared minus n over 2. Standard. That's our assumption. Then we have, for n being larger than 1, right? We're going to say 4fn over 2 plus n, and then we're going to recursively put another one in there, and we're going to say 4 times 4n over 2 squared minus n over 2 plus n. That's from our inductive hypothesis, right? So it's going to be 4 times 4 times n over 2 squared minus 2n plus n, and then you're going to go to another row of cleaning it up. And then, you do the same thing, another line, and that turns out to be 4 times n squared minus 2n plus n, because the 4's, cancel out one of the 4's. And then, we clean that up, and it's going to become, in the last line, 4n squared minus n. And that proved our case for mathematical induction. All right, guys, that will be all for this question. I'll see you guys in the next one.